welcome to another math video. And today we're going to talk about some matrix operations, and we will see some proofs of some of the properties that these operations have. Right, so matrix operations. First, let's look at matrix multiplication. And so let's assume we have one matrix A, which is in the real numbers, and it has the shape n times n. So that means it has m rows and n columns. And then we have a second matrix, and this has n rows and k columns. And it's important that these two numbers match. And in this case we can define the product, which will then be in our mk, so it will have n rows and k columns. And just so you're all familiar with how matrix notation works, let's write down an example matrix A. So let's assume it has two columns. So example, then the indexing of the entries works like this. So the first one in the upper left will be 1, 1, and then the one below will be 2, 1. So it will be in the second row, but still in the first column. Then this continues, so in the first row they all have the first number 1, and then 2 and 3 for the second and third column, and the same in the second row. So that's how the indexing works, and similar it would work for B. So the product definition will be per entry. So the entry ij in the ith row and j column will be defined as follows. We will take the sum from, let's say, L1 up to n. That's the common length, the common dimension. And then we go through the ith row for this entry in A, and we go through it, so that's the running index L, and we go through the jth column in B, and we go through it with L again, and then we sum all of these up, and that is our entry for AB. So let's give you a more concrete example, because this looks rather weird, but we'll need this later on to prove it. But let's say we have a concrete example with one of the matrices, which is A, is 2, 0, 1, 1, 3, 4, and the second one will be 1, 1, 2, 4, 0, 3. And now for the product, I can put a point between, but we usually don't. We will go for the first entry on the upper left, we will go through the first column and the first row respectively. So we will do 2 times 1, which will be 2, and then 0 times 2, which is 0, and then 1 times 0, which again is 0. So the sum of all of these will remain 2. And now the entry below that will be the second row, and still the first column, because we're still in the first column of the result. So this will be 1 times 1 plus 3 times 2, which is 6, and then 4 times 0, so that's 0 again. So now we went through all the rows in the first column, and now we go through all the rows again, but in the second column to create the second column of the result. So 2 times 1 is 2, 0 times 4 is 0, and 1 times 3 is 3, and the one below is 1 times 1 is 1, and 3 times 4 is 12, and 4 times 3 is of course also 12. Now we can write the complete answer. That's 2, 5, 7, and 25. And I hope I didn't make a mistake there. Alright, and now let's also look at matrix addition. For this, A and B need to be the same shape, and then A plus B again per entry is defined as just the ij entry from A plus the ij entry from B, so it's just entry wise. So here the example, let's take 2, 1, 3, 0, and add 5, 7, 0, 4, and that is then for the upper left 2 plus 5, below that 3 plus 0, so always the entry respectively, and then 1 plus 7, and 0 plus 4. And that's 7, 8, 3, and 4. Alright, now that we have all the examples and definitions in place, let's look at some property. The first is matrix multiplication is distributive. And that means that A plus B times C is the same as AC plus BC. And that might look very familiar because, of course, that is true for the normal real numbers that we're working with. But because matrices are different and we have just defined new operations on them, we need to prove that this is the case before we can use it. So let's do this and prove this entry-wise. It's a rather short proof. It's basically a one-liner, but we still call it a proof. So we take the entry of the left one, A plus B times C ij, and at first we will use the definition for the multiplication. So for that we go over L, like here, and I haven't defined the sizes, so we just leave this empty, but we go over L, and we go over the matrix, over this matrix, which we haven't written out yet, but we go through it I, L, like up here, so these are the indices, and then C, L, J, like up here was the B. Alright, and now the next step is of course to use the definition for the addition here, which we have up here. So we still have the sum, and in here we can now say A I L plus B I L, and this stays in brackets, and the whole thing is multiplied by C L J. And now, because these are just real numbers, we can use the distributive property of the real numbers and say this is the same as A times C and B times C. And now we can use the property of the sum, that we can split it up into two separate sums, because the sum of real numbers is commutative, so you can switch the order in which you sum things up. It doesn't change anything. So we will first sum up all of the A's and C's, and then sum up all of the B's and C's. And now you see that these, you can barely see, need to put this a bit higher. Now you can see that this is exactly the definition of AC plus BC. So, and then of course the ijth entry of that. So we have proven that matrix multiplication is indeed distributive. Now we can also prove that matrix multiplication is associative. I think that's how you say it. And what does that mean? That means if we take, I hope I'm not blocking everything with my hands, but use your imagination. That means that when we take first A times B and then times C, that's the same as first doing B times C and then multiplying A from the left. So the order in which we do these doesn't matter, but the order of multiplication does, so we can switch them. So AB is not generally the same for BA. So this doesn't hold for all. It could be true for some matrices, but for most of them this is not true. But if we first multiply the left or the right two, that is the same. And of course we can also prove that. But first let's define the shapes of these so we don't get as confused. So let's say A has m rows and n columns. Then of course this has to mean that B has n rows. Otherwise we couldn't multiply them. It wouldn't be defined. Let's say it has p columns. And C has then of course p columns, because otherwise it wouldn't match. And let's say Q columns. And to verify that when we first multiply these, the shapes still match up, we can also say that AB is of course from the shape MP, so the middle one will go away and we will have the same number of rows as A and the same number of columns as B, which is P. So this is m times p, and then we can multiply it with the c, which is p times q of a shape. So these are these two, and these two, BC, has the shape nq, which is still multiplicable, able to be multiplied, that's the word, with a from the left, because n and n is the same. Alright, now let's get into the proof. So AB times C, and we again look at it entry-wise. So the entry ij is defined as going through the shared dimension of A and B. Oh no, first we will define or use the definition for the outer multiplication. So the shared dimension of AB and C is the P. So we go L equal 1 up to P, and we take the entry IL of the first matrix, which is this product, and Lj of the second matrix, which is C. And now we can dissolve the inner product. And we keep the outer sum, of course, L up to P. And now we go through the shared dimension of A and B, which is N. And we do it with K, slowly running out of numbers, letters, same thing. And we go up to N, like I said, the shared dimension. And of these, we now need to be careful because we have IL outside. So the fixed entry is I, like before in the definition. So AI, and the running index is the K from the sum. And then B is KL. This is our running entry K, and L from this outside. Normally we have IJ, but here in this formula we have IL. My K's are a bit ugly, you have to forgive me. And the outer thing, the C, LJ, stays the same. And now we can, this is just a product, and the real numbers are also distributive, so we can pull the C and we can multiply it with every single one of these parts of the sum. So this is L, and if you would do this proof as homework or something, you should probably for each significant equal sign you should write down what property you used, especially if you're in one of the first semesters in university. So this is, like I said, the distributive property of the real numbers in this case. So that's I, K, B, K, L, C, L, J. And now I have already written this down, so we can do it a bit fancier. We can just continue from this. But if you are doing this for the first time, you might have to write down the other side and pull this out again, and then you will arrive at the same thing. But we can do it backwards from here, so it stays in one nice flow. It's always very nice. So here we can of course do the same thing backwards that we just did with the C. Oh no, first step is we can switch these sums around, because again it doesn't matter in which order we add things. So we can put the N sum out and the P sum inside. I, K, B, K, L, C, L, J. And now, because this A doesn't depend on the L, we can pull it outside because, again, distributive property of the real numbers. But you have to be careful that it doesn't depend on the index, because otherwise out here the L is no longer defined, so we couldn't pull the B out because it changes based on this index, but the A doesn't change based on the L. So we can pull it out of the inner sum. That's one. A, I, K. And we keep the inner sum. And now put parentheses above this, around this. And now this here is the product of matrix B and C if you look back to the definition. So the whole thing then becomes I, K, A, I, K, and then B, C, and then this is the entry K, J, and L is the running index, so this is K, J. And now this is again the product, the K's are the same, so this is the entry IJ of the matrix A, B, C. So we have shown that each entry of these matrices is the same. And if each entry is the same, then we can also, so each entry of A, B, C and A, B, C is the same. Therefore, A, B, C and A, B, C are the same. So that will be just a sentence to make sure that you don't get any points taken away from your homework. And you could also write this, of course, on the previous page. And then you can write this tiny little square. That means that you have proven something, but I would recommend to not do this on your homework because it's a bit pretentious in my opinion, but that's just me. Do whatever you want. Alright, that's it for this video. I hope you liked the variety of recording on paper. Thank you so much for watching, and I'll see you in the next one. Bye!